of all, good morning to all NET set aspirants who are willing to crack the different exams like NET, SET, or just GATE exams. So first of all, I would like to congratulate the organizing team of the SGM College Karad, especially the principal Rajmane sir. Under his leadership, the college has done several activities, and during this, all of us are stuck at our homes due to this global COVID-19 pandemic. So it's better for all the students to revise, to restructure, to just brush up all things which we have studied in previously. So right now, the NET June 2020 exam is also not held due to this COVID-19. So all of you are preparing, I think, from last December, and the main thing is today, from last 3 days, as this is now the fourth day. From last 3 days, all of you are studying about this NET SET exams subjects. The Pawar sir has introduced the classical and quantum mechanics. Second, the Nadgowda sir introduced about the ED, electrodynamics. Then yesterday the Gaikwad sir also given lecture on the electronics. So basically, so now most of you have got the enough idea about the what is the main exam, what are the points which you need to be covered, and what are the things which we need to look up. The main important points are the crux, because all of you are now postgraduate students. Maybe some of you are pursuing your MSc right now. All of you are the basic ideas. All of you know the reference books. But just because in 1 year ago I used to on your side, on that side. So I know the very much basic things. So what are the problems? What are the difficulties? And the main crux. We don't need to cover all the syllabus, because as Ram Baur sir mentioned, the NET exam is all about the 280 marks, and we just want around 80 or 100 marks. So 1/3 marks. So what we need to do, you have to just strengthen your subject. You have to choose which subject you like your most. Okay, and you have to focus on that subject. So today, I am going to deliver a lecture on these solid state physics and nuclear physics part. So let me share my screen. Okay, is it visible, Dole sir?
Yes, sir. Okay.
Okay.
Yes, sir.
Okay. So the objective of my today's talk will be what the plan and strategies for NET SET exam, syllabus for the NET SET exams, and examples related to this NET SET exam. So main thing, all of you are aware about the NET SET exam. Most of you are given lots of exams, 2 or 3, or second attempt, third attempt, and some of you are just in a MSc or willing to give the exams. But the main thing about this objective, I will go to the syllabus later on about the solid state and nuclear physics. But the plan and strategy, that is the very much important thing when you prepare for such a different exam like NET, SET, GATE, JEST, any exams. So in that case, the main thing is for the NET exam or SET exam. Okay, this is a national webinar. Again, I repeat. So most of you are from outside Maharashtra, also from different states. So I am talking about the Maharashtra SET exam, because lots of students are from the Maharashtra. But the CSIR-NET is all over India, so it's common. Now, when I have given the exam, that time the exam was written based, means you have to go and mark the OMR sheets and you will get some mark. Now from last December 2019, it was handed over to the NTA, National Testing Agency, and it was held online. So now you are under that countdown time continuously. So it's again different strategy. So time management is very much important aspect now to crack the exam. So first thing I would like to share with you about the NET exam. Most of us are afraid about this NET exam. Means what we think, it's very much difficult. It's not high preparation. It's need more conceptual knowledge. Okay, that is also main required. But main thing, as I mentioned, apart from 280 marks, the full marks, paper is 200 marks with optional, it's around 280 marks. So around 280 marks, you have to just score 80 marks, 80 or 100 marks. 100 mark is a safe merit. As I mentioned, if you score 100 marks, definitely and definitely you will get LS minimum lectureship, and you will get JRF if the merit goes down. But now the time management is most crucial factor. So for NET exam, what you need to do first, you have to first look at the syllabus, or you have to plan what are the things, what is the syllabus, what are the different criteria, what is the last merit, last 5-year merit or 3-year merit, we can say, because it held twice in a year. So you can say, you can just refer the last 3-year papers. So the main thing is the self-confidence, which I again repeat, self-confidence is very much important. You have to believe yourself. You have to tell yourself that NET set exam is very much easy, and I will do that. Whatever hard work I have to do, because there is no option for the hard work. You have to practice and practice more, and you have to focus on the subjects which you like most, or which you are good, very good. Then next case is about the syllabus of NET set exam. So I will mainly focus in that category. I will mainly focus about this solid state physics and nuclear physics, and then we will solve the recent examples of the NET set exams which are come in last 3 years, or let's say from 6 papers, we can say, because it's organized twice in a year. So first we will cover about the solid state physics. So what comes in your mind? Solid state physics. It's a branch which needs with material science. So either when you qualify your CSIR-NET, LS or JRF, whenever you go, you will require this subject, because this subject is the bridge between the theoretical and experimental physicist. Because unless and until you don't know about this material science, you can't pursue your career in PhD after the qualifying the exams. So first I will go for the syllabus for NET for the solid state physics or condensed matter physics, we can say. So for solid state physics, the red one which I have marked, the red one in NET and SET, the bottom one is the syllabus for the Maharashtra SET. So the red points explain these common things, okay, the common things which you need to prepare. So most of are saying, sir, we are preparing for the SET, we are not preparing for the NET, like the MPSC, we can say, we are preparing for MPSC, not for MPSC. But main thing I have to mention, the physics is same throughout this, just the pattern is different, like the matches we play, one day T20 test, okay. The syllabus is same, what you need to do, and very much important concept is concept understanding, and the everyone, any part which will help you in the exam. Let's say if I prepare the reciprocal lattice, the first concept, syllabus for NET. Now it's not in this syllabus or not in the GATE exam, but it will definitely help you in qualifying the JEST exam or a GATE exam. So it's not at all wasted. It will help you surely in future anywhere. Means if you go further for the lectureship or further research career, it will help you. So first of all, the red points which are marks, highlights, those are the common things. So what you need to do, you have to just go one by one from the topic. Now all of you are aware, all of you have smartphones, Google's high-speed internet. You can search all the things. There are lots of online courses, online sites. Now in this lockdown, there are more sites developed by the MHRD. It's the virtual lab is there, NPTEL is there, Coursera you can do. So there are lots of lectures. Either you can search on Google or YouTube, you will get these lectures. Next, these are some reference books which I will suggest to refer. The first one is Ashok Marbin, which is the very much important book. The fundamental book which you need to prepare, if you go for the solid state physics, you need to refer this book, S.O. Pillai book. Okay. Then I will suggest, now depend upon difficulty or the interest which you are in. If you are more interested, you can go to the Kittle. And the main thing which I refer you is this series. So all of you, please take screenshot of this. You can download it. It's free. It's available on the Google. The problem and solution by Yung Pyo Lim. It's also known as the YK Lim series. Again, I repeat, it's YK Lim series. So it's very much important. It's much more effective. If you solve the problems from this book, you will definitely crack any exam. NET, SET, GATE, JEST, any exam, whatever exams you will do, or those who want to pursue your career after calling exams in BRC, IITs, whatever the public sector units, ONGC is there. Then there is one book which is numerical problems in solid state physics by MA1. This is the problem based solutions. So there are almost around 5,500 problems. So you can refer also that. So what it knows, the practice makes man perfect. So more you solve, more problems, more different types you solve, the more you will get idea about this case. Now, before going to this solid state physics, what I will do uh, for the NET exam, CSIR-NET. All of you are aware. Now someone saying the reference last year, sir, this is come for 18 marks, this is come for 20 marks. But for solid state physics, exam pattern is same. There are three sections A, B, C, in which C section is of 5 marks, and every year solid state physics is come for 15 marks. 3 questions of 5 marks each. Okay, so there is no need to worry how much it will come. There is definitely will get 15 marks, surely. Same thing for the nuclear. That's why I have not introduced this pattern last year. How much weightage is there? So there is no need of this. You have to remember both subjects come for 30 marks, 15 marks for solid state physics, 15 marks for nuclear physics. And it's always at this, what we can say, back page, last page. So what I have done whenever I go for the exam, because these are the main basic points. Unless and until you will more take risk in part C, you will not qualify the exams. Remember, because the part A is aptitude one. So people are normally what they are doing, just whenever they go for the exam, they are doing just part A. They are solving the problems, and later on they recognize they have got the marks almost 10, 12 points correct, but they have wasted the 45 minutes, almost 30, 45 minutes. Or in part B, they are wasted 4 marks. But at the same time, if you are given in the part C, you will get plus 5 marks for each question. So again, remember, if you have to qualify the exam, especially for the JRF, Junior Research Fellowships, it has the different merit. Around plus 10 marks is varying for the different category purpose. So the main thing, you have to focus on the part C question. Again, I repeat, you have to focus on part C part. Unless and until you will not cover minimum 50 marks, we are expecting from part C, means 10 questions, and you can easily solve. For solid state, there are 3 questions. Nuclear physics, there are 3 questions, so 6 questions is there, it will give 30 marks. And in aptitude, there are some questions which are very basic, means normally in 10 minutes you can solve 4 questions. There are mirror image problem, sequential series problems, so that you can solve. But what I will refer you, all of you, for the whatever NET aspirants which are preparing for the exams, that you have to focus on the part C. When I qualified the exam, I have got around 17 questions correct in part C. So that's why I got 85 marks just in part C. And the rest of the one I will get, and I have qualified the exam. So main thing that is very important. So time is very important. So depending upon your choice, the first 5 minutes you have to look up for this paper. Just look at the glimpse. What are the papers? What are the difficulties? And from part C, and in solid state physics and nuclear physics, what you need to do, if you know the basic concepts, you will, and some examples or some shortcuts that I will show you, or the smart tricks from these, the crux or the cream part of this syllabus. So then and then only you will get easily marks without wasting too much time. Because in quantum question is also there in part C. Let's say variational method is there. You have to choose the wave function. You have to calculate kinetic energy, potential energy, take derivative, and substitute that values. You will get the answer. So that is too much consuming, time consuming, and you will get 5 marks. But at the same time, if you are given in this category, you will get easily 10 marks in that same particular time. So I again request all of you to go for these books, Pillai book. Then next one is Ashraf Marmin and Charles Kittle. And this series you can download from this internet. You will get it. It's available free. It is YK link series. Okay. And these are some useful sites for the syllabus. This is the CSIR-NET, and this is the SET exam for the Maharashtra SET in Pune. It is organized by the Pune University. Okay. So next, now what I will do, I will not go into the details of all this solid state physics. What I will do, I will just make a crux, or we can say the glimpses of the syllabus, the main important points, which will definitely come in the exams. You don't need to prepare all the things. Just focus on this. So basically, there are types of lattice in 3 dimensions. So all of you are the lattice is what? It is the periodic arrangement of infinite number of points in 3-dimensional space. Okay, that space is reciprocal space, and that lattice is also known as Bravais lattice or space lattice. If each lattice point has an identical surrounding, means we are considering the dots like we draw a rangoli on these uh, dot patterns. So if you consider the each lattice point, if it has identical surrounding, then that lattice is known as Bravais lattice or space lattice. Then the question comes the basis or motive. Somewhat some books refer the motive or MOTI motive. The basis is what? An atom or group of atoms which is attached to the lattice points, known as the basis. It may be monatomic, diatomic, or triatomic. And the lattice plus basis forms the crystal structure. Again, I repeat, the lattice plus basis forms the crystal structure. So there are 7 types of crystal structure, as you can see on the screen. First one is cubic, tetragonal, orthorhombic, trigonal, hexagonal, monoclinic, triclinic. So whenever you go from the cubic to triclinic, the stability goes on decreasing. Okay, and these are the 14 Bravais lattices, which I will go in deeper in next few slides. And these are the condition: alpha, beta, A, B, C, and alpha, beta, gamma. A, B, C are the lattice parameters. So all of you are aware. Just for this, those who are MSc, right, going pursuing the MSc, for those, this is the important things. Then there are types of lattice in 2 dimensions. So there are different types of lattices in 2 dimensions. In 3 dimensions, what we have seen, there are 14 Bravais lattices. And in 2 dimensions, we are getting the square, rectangular primitive, rectangular center, hexagonal primitive, oblique primitive. Now, unit cell. Okay, before going to the next, I will focus on the unit cell. So what is unit cell? It is the smallest part of the crystal which on continuous repetition generates whole crystal structure. So imagine a wall, normal wall, window wall, and the bricks in that wall, each bricks is a unit cell. If you go on combining the unit cell on the continuous repetition, you will generate a wall. So that mostly clear on the concepts. So the individual unit cell, the smallest part of that wall, that is brick, is termed as a unit cell. So that is the main important thing. Then next is there are types of different unit cell. First one is primitive, second one is non-primitive. So in primitive unit cell, the number of lattice point, if it is 1, again I repeat, if the number of lattice point is 1, then that cell is known as primitive unit cell. If you consider a unit cell normally, let's say there are atoms which are at the corner. Now the number of lattice point per unit cell is 1 because each corner atom is shared by the 8 cubes. So number of lattice points per unit cell is 1. So that is the primitive unit cell, which is the simple cubic structure. For body centered, what you need to do? There are atoms at the corner and one atom is at the center. So the number of atom cell is per unit cell is 2. And for face center, the number of atoms per unit cell is 4 because the atom for the corner, which is 1, and the atoms which are at the face, which is one atom which is shared by the 2 cubes. So you will get that 3. So number of atoms per unit cell is 4. So the main thing from that is the simple cubic cell. We can say that is the primitive unit cell, or non-primitive unit cell, which consists of the body center and face center. Okay. The next. Okay. Then we will go about this 3 dimension. Okay. 3 electron theory. So there are different models. I will not go into the details due to the time constraint. There are 3 electron theories there. Root model is there. Debye model is there. Then Einstein model is there. So the for free electron theory, what is that? The Fermi energy, which is equal to the p square by 2m, or we can say the in momentum space, what we can say h cross square k square by 2m. Okay, and the Fermi energy is what? The highest occupied energy level at which the all electrons are filled at 0 Kelvin. Okay, and means for the metal, whenever you excite the electrons or whenever you provide thermal energy, electron will excite or not out from the Fermi energy, not from the inertia. Fermi energy is the topmost occupied level at which electron is filled at 0 Kelvin. Remember, at 0 Kelvin. And the energy required to remove that electron from the Fermi energy to outer space, or we can say free space, is known as work function. So whenever you provide the work function amount of energy, it's like simple 1D box. Is the Fermi energy at this point? If you provide this amount of energy, then that electron will goes out. Then after that, the Sommerfeld model considered as I mentioned, it is the apart from 1D oscillator, he has considered the one-dimensional box. So using that boundary condition, the Schrodinger equation, you will get this equation, the boundary condition. You will get the Fermi wave vector equation, which is n pi by 2l. Okay, and P is what? As I mentioned, h cross k. It's in momentum space, or we can say reciprocal space. Why it is known as the reciprocal space? Because the reciprocal space is always in wave vector k. K is what? Wave vector. It is 2 pi by lambda. In normal, we will say the unit in lambda. In reciprocal space, you have to reverse 1 by lambda. Why reciprocal space is required? It is the imaginary concept, because in normal space, the atoms or lattice points are attached close to the another. So we can't differentiate. We can imagine the structure. Whatever structure we have said, simple cubic or BCC. What we are assuming, the atom is one atom is at here at this point, one atom is at this point, and we are get the separation A, B, C. Whatever just we are just think. So the main thing is reciprocal space mu naught. It is 1 by lambda. So what it will do? It is the 1 by lambda. So it will resolve the structure. For the imaginary concept, for the visual understanding, it has done. And from that point, you can extract the all other points. There's the Fermi velocity, Fermi temperature. This is the Fermi temperature, E up by K. Okay, which is E is equal to KT, which is K is what? The Boltzmann constant, and T is the room temperature, which is the room temperature thermal energy for any molecule. Let's say this is one molecule. What it consists of? It has some thermal energy at room temperature also without supplying energy. It is KT. It is 25 milli electron volt. Again, I repeat, it is 25 milli electron volt. So any atom having the energy is KT. E is equal to KT at room temperature. Okay, so those who are interested, they can take screenshot. So it will there will be useful for them for the formulas. Okay, from that point, what we can do? Yes, sir.
Sorry for interruption. Some yellow window is coming in that slides. Can we remove that?
Just wait. I will share again. Okay, is it okay?
Yeah, now it's okay.
Okay, thank you.
Okay, please continue, sir.
Okay. Okay, so things which we have discussed. Just a minute. I will make mark. Okay. So from that point, what you will do, you can date for the one dimension. This is the Fermi wave vector, and how it's calculated using Sommerfeld model and Schrodinger equation. Using the boundary condition, you will get this equation. From that K, what you need to do, you have to just remember this point K, wave vector. From that point, you can extract all other factors: Fermi energy, velocity, momentum, temperature, density of states. Okay, this is the thing which is very important. So those who are interested, they can take screenshots. So it will be useful for them. Now, for the density of state, what you require, the number of electrons in that present level per unit area. We can say the density of states. Now again, there is lots of too much lengthy equation. After that, you will get this relation. For 1D, it is proportional to e raised to minus half. 2-dimensional, it is independent of energy, and in 3 dimension, it is proportional to the half. But the main thing which we can do is using this equation. Okay, so this is the, apart from doing all those things, what you need to do, if you have to ask the density of state with energy relation, you just use this formula, where e raised to d upon s minus d by s minus 1, it's separate, okay, not s minus 1, d by s minus 1, whereas d is dimension and s is the power of k. So what is the power of k? We will go into details in next few slides. This is the energy dispersion relation or frequency dispersion relation, which is in omega and k. Next, okay, so these are the things just I mentioned. It is total number of electronic state, density of state, coordinate interval, or this n equal to 2n's. Why that factor 2 comes? Because due to the Pauli exclusion principle, no two quantum numbers have same n, l, m, l, m as value. That is principal quantum number, azimuthal, orbital quantum number, and spin quantum number. So if you have to place the two electrons for the fermions, one is spin up and another is spin down. Then and then only you can place those electrons. You can place more than two electrons. So by solving this equation, by taking the derivative with number of particles and using that 2n factors, you will get this relation e raised to minus half. Okay. But if you use this formula, you will definitely directly get this equation. You don't need to solve all these points. This is for 1D, 2D, 3D. You need to solve all these equations. So no need to do that. Okay. Now for the graphene, which is the two-dimensional structure, which has the honeycomb structure, I can say it has having the dispersion relation E is equal to CK. Now previously slide, when we go, what we observe, E is equal to h cross square k square by 2m. This is for the fermions. Fermions basically they are electrons which obeys the Fermi-Dirac statistics. So E is proportional to k square. That's why you are getting the parabolic shape. If you draw the EK curve for this electronic or the fermions, you will get the parabolic shape. Okay, we will go into the details in few slides because it's similar like the y square equal to 4x. It's like the parabolic equation. That's why you are getting this curve shape. For the graphene, it's CK. Just remember, it's related with the K proportional, not the K square. If you know this, you can again extract the same thing: momentum, temperature, energy equivalent area, density. Just what you need to do, you have to just know the relations, or you have to just remember the equation, I can say. But it is not very difficult, too much task. For the electron, it is proportional to k square. Graphene, it is proportional to k. The magnon, which is the spin quantized wave, it is again proportional to k. Only three parts are there. Okay. For bosons, which whenever you have the massless particles or very less mass, you will get the dispersion relation which is proportional to k. For boson, photon, phonon, it is proportional to k, or graphene. And for electron, only k square is there. Okay. Okay. Next point. So for just we have looked at one dimensional, the density of states, which is the e raised to minus half, e raised to 0, e raised to plus half. And if you have to calculate, now look at this part, bottom part, specific heat. Okay, which is the amount of heat required. Okay, there are latent specific heat, molar specific heat. There are different parts, but this is the main is the amount of heat which requires to raise the temperature of, let's say, unit mass of substance by 1 degree Celsius. So if you are to ask in exams, okay, we will later solve the examples, so you will get no idea about these examples. For the bosons, remember, for the bosons, it's proportional to K. Again, I repeat, bosons, photons, phonons, magnons, and graphene, it is proportional to K. And for fermions, it is proportional to K square. If you know this, you can extract all the parameters. You don't need to solve all those lengthy equations. So for that, the specific heat is proportional to D. Now, what is the D? It is the power of K. Now, in this case, the power of K is 1. So it is T raised to 2, T raised to 3. Now, in case of bosons or fermions, we can say it is D by N. Okay. So dimension is 1 and power of K is 2. So that's why you are getting T raised to 1 half, 2 by 2, 1, and next thing. Now, the next thing which I would like to focus is on the energy dispersion relation. So whenever you solve all those things, energy dispersion relation for free electron, again I repeat, free electron is equal to k square. That's why you're getting the parabolic shape, which is the similar like parabolic curve. Now, whenever an electron moves into the solids, normally what we are consider in initial case, it is the free electron. It has the parabolic potential. Now, whenever that electron goes into the solids, it interacts with the lattice potential. There is one theorem which is known as Bloch's theorem. What it says, there is periodic potential. If you have calculated the potential at a particular point, let's say V of x, and after some particular interval at V of x plus a, the potential will be same. That is the Bloch potential. And there are some factors which you can look. This is the first Brillouin zone, or we can say Wigner's scale. This concept you should know definitely. How to draw Brillouin zone? All of you are aware about this. Still, I will let you know. In first case, we have considered the lattice point. You have to collect all the lattice points, then draw the perpendicular to the lattice point. Then, whatever area you are getting, that is the smallest or minimum area under the curve, which is the first Brillouin zone, we can say first Brillouin zone. And using that condition, Sommerfeld model, again, I will like to refer all of you the Kittel book. In this, all these figures are mentioned, all these derivations are mentioned, but I will not go into details. So there is opening of the band gap at a particular point. You can see this. It is plus minus pi by for 2 pi by for the second Brillouin zone. Is this the first Brillouin zone? Minus pi by to plus pi by, at which your Bragg's diffraction condition satisfied. Okay, Bragg's law, all of you are aware about this XRD, X-ray diffraction pattern. Bragg's law 2D sin theta equal to n lambda, but that is in real space. Okay, again I repeat, that is in real space. If you go for the reciprocal space, what you have to do, you have to consider the evolved sphere. There are wave vectors, and the condition which you are getting, that is 2k dot g plus g square equal to 0. What it does, where k is your wave vector. So this is the reciprocal lattice condition. So just remember the main thing, at the Brillouin zone, the Bragg diffraction condition should be satisfied. Okay, so that is the opening of the band gap at plus minus pi by, plus minus pi by or 2 pi by. There is one other concept which is known as the effective mass. Okay, effective mass. Now, effective mass is basically whenever now electron is free to move normally. Whenever it goes into the lattice, it interacts with lattice potential, and if that electron is moved, then hole is remaining. Absence of electron is hole. That hole is less mobile compared to the electrons. That we are term is effective mass. We'll go into details in few slides. So the formula for this is this one: h cross square by d square e by dk square, which is the second derivative of this ek curve. What is the ek curve? This is the ek curve. This is the dispersion relation for the energy ek curve. If that graph is omega versus k, and there is dispersion relation for the frequency. Okay. So relation between E and K or omega and K is known as dispersion relation. Okay. Next thing, if you take the single derivative of this with respect to dispersion curve of the omega and K, you will get this formula, that is the 1 by h cross dy by dy by k. Okay. We will not go into details. I would like to refer you all this solid state Kittel book by Kittel. Okay. This is the double derivative, we can say, for this. What you can observe, this is the velocity single derivative for this ek curve, the first curve which are drawn, this curve. If you take the first derivative, you get those points at plus minus pi by, again the boundary condition are satisfied. So as you get this formula Vg, that is the group velocity, you can say, or Bloch velocity. Whenever that electron goes into the lattice, that electron is known as Bloch electron. Someone was referring, what is Sir Bloch, where is the free electron? Electron blows into the lattice, it is termed as a Bloch electron or Bloch theory. Based on that, you will get the Bloch theorem. So if that slope is increased, your Vg is increased. In that case, if your slope is increases, Vg is increases, group velocity. Now look at this graph, first graph. It's very important. So at the bottom, this is the point of inflection. Means what? At this point, you will get the slope 0. If you take the derivative at this point, you will get the 0. So at the bottom of the point, effective mass is always positive. Okay. Again, this is for k square. We are now looking at these electrons only, fermions. Okay. At the midpoint of the curve, at this point, this is the point at the midpoint of the curve. Okay. What you will get? Dy by dy by k is constant, because if you take the derivative at this point, you will get the constant. And effective mass is infinity, which is known as the point of inflection. This point of inflection. And the top of the band, you will get the effective mass negative. So those things, again, I think these are the important things. Again, I refer you all to go for the reference books, which is the again YK series and the Kittel, in order to clear your these basic concepts. Now there are number of branches in solids. Okay. Now the optical branch and acoustic branch. Now what I will suggest you for this, whenever we are considering the lattice or basis or phonon, lattice vibrations which are known as the phonons. So there are interaction of the lattice points with respect to the temperature. If that is lattice is vibrate around this position, you will get about these thermal properties or specific heat. And if it is imposed, or we can say applied by the force frequency or external energy, then it leads to this different two, acoustic, which is known as the sound, we can say acoustic one, and the electromagnetic, that is the optical. There are two different modes. Again, for details, you should refer the books. I will not go into details. So we are getting the two optical branches, acoustic and optical branches. For the acoustic, as we know, sound wave energy, it's propagates along the direction of the wave, and in optical wave, it propagates along the direction of wave, perpendicular to the vibrations. Means wave is like this. You are the light vectors, or we can say the transverse vectors, which are perpendicular to this direction. So look at this case, first case. For the number of branches in the solids, for p atom, primitive unit vector p atom basis, if you have the one acoustic branch, optical branches are p minus 1. Again, this is the crux, what we can say, the or important points from this, or lots of derivation, 2-3 page derivations. So again, I request you all to take the screenshot, so better you will help in the exams. So for the monatomic lattice, if for monatomic lattice the primitive unit cell point is 1, the optical point which you are getting the 0. Okay, same thing for all, you can calculate easily. Now the number of modes of vibrations. If there are p atoms in primitive unit cell, again the primitive unit cell, which is what? The number of lattice point per unit cell is 1, means which you are considering the simple cubic unit cell. For 1D, it is the n optical branches we are getting is p minus 1 into n, where n is what? The total primitive unit cell, means let's say for formula units, for B80IO3, means you can place the B80IO3 molecule in 1 unit cell. If you go for the cobalt ferrite, you will require 8 unit cells, means formula structure, we can say number of atoms per cell which required is 8 for cobalt ferrite. So in this case, it is 2p minus 2 and 3p minus 3. From that, you can easily calculate the number of acoustic branches and optical branches. Again, I will not go into details for these two dimensions. Same thing you have to refer. Now, this is the dispersion relation, the bottom thing which you can see. Okay, so this is dispersion relation for one-dimensional monatomic lattice. Again, there is lots of derivations using the Sommerfeld models, Schrodinger equation. The final equation which you are getting is this. Okay. Then the second term is the geometrical structure factor. Okay. I have written the direct formula, but before that, I will divide that about this. Now, in XRD, whenever there is diffraction takes place, diffraction is what? Let's say if you have lattice, when the diffraction will takes place, if your incident wavelength is comparable to the interplanar spacing, then and then only it will get the diffraction. So diffraction is basically the special type of scattering, we can say. Whenever this condition is satisfied, all of you are saying, once we ask the students what is the diffraction condition, they said 2d sin theta equal to n lambda. No, the main diffraction condition is your lambda should be equivalent to the interplanar spacing. That's why for the diffraction we are using the X-ray, because the normal interplanar spacing between the crystals is lies in the 1 to 10 angstrom, you can say, and the X-ray wavelength having the same range, 1 to 10 angstrom. That's why we will get the diffraction pattern. That's why X-rays are used to study the diffraction pattern. Next thing, now X-ray, let's say incident on this different unit cell, simple cubic cell, body center unit cell, and there is what term HKL. What is HKL? It is the Miller indices, which tells you about the orientation of the planes. What are the planes present in the crystals? If it is a single crystal, then all planes are oriented in particular direction. Let's say this is oriented in one direction, so you will get this 0, 0, 1 in z direction. For polycrystalline, you will get a different orientation in the plane. And Miller indices is calculated using the by taking the reciprocal of the intercepts at which it cut the axis A, B, C or XYZ axis, we can say. Now for simple cubic, what you need to do for simple cubic, all HKL values are allowed. Means or the simple cubic in itself, if that HKL, let's say Miller indices are 111 or 122 or anything 333, or how you can write 333 means what? It's 3 into, here we can say 111 means what? If it is 111, 222 is there, means it is parallel to 111, 222 and 333 means whatever reflection we are getting from 111, it is same as 333. Okay, just the intensity is different in this point, but the brag position, or we can say in XRD, if you go in the intensity versus 2 theta, the angle position 2 theta, you will get at the same point. That's why you are getting some broadened peak, that heighted peak, somewhat or less. But the intensity, if you look at the XRD, it is the arbitrary unit. It may vary with respect to sample, with respect to pellets. Now, for the body centered, the coordinates which you require, U, V, W are the coordinates which you require are these 0, 0, 0 means at the corner, and at the center atom is there, half, half, half. For that case, again, I will not go into details. Your H plus K plus L value should be even. Again, I repeat, for simple cubic, all HKL value allowed, means H plus K plus L anywhere. It is either even or either odd or either mix. For body centered, it should be even, means H plus K plus L should be even. And for face centered, means let's say this is the cube, atom is at the face, which is having coordinate 0, half, half, or half, 0, half, or half, half, 0, anything. So for that case, your H plus K or K plus L or H plus L should be either even or either odd. Then and then only you will get the peaks, diffraction peaks, at which the boundary condition is satisfied. And this is the structure factor. What is the structure factor? There are two factors actually. One is the atomic form factor, and another is structure factor. Atomic factor is what? The scattering of the atoms. Okay, amount of scattering by the atoms to the scattering by the individual electron. And if you summarize or take the summation, you will get the structure factor. Now, whatever pattern you are getting in the XRD, that is depend upon the different factors. So structure factor is there, and the intensity what you are getting is proportional to the square of the structure factor. It is proportional to F square, capital F square, and it is again depend upon the temperature, Lorentz polarization factor, multiplicity factor, atomic factor, and structure factor. There are 5 factors which are dependent, or which we can say the intensity of the XRD is depends upon the 5 factor. Again, I repeat: atomic factor, structure factor, Lorentz polarization factor. Means what? It is assumed that whatever light coming from the X-ray tube, which is incident on the sample, it is plainly polarized. Means what? Plane polarized. All dipoles are perpendicular to each other. Whatever the movements, or we can see whatever light is perpendicular to each other. Then the multiplicity factor, the planes which you are considered just, that the 333, 111, 222, it may be 11, 11, 11. Okay, so it is same as 111, no problem. And then the second is temperature factor. With respect to temperature, what you can get? Hello, Dole sir.
Hello, sir.
Is it visible?
Yes, sir.
Yes, yes.
Okay. Okay. Just wait. Some problem is there. I can share again. Okay. So for that, FCC structure, H plus K, K plus L, or H plus L should be either even or either odd. Then and then only you will get this FCC peak. Means for face center cubic, this condition should be satisfied. Then we will go into this main part, the diffusion length, we can say. Again, I will not go into the details. Diffusion length. Diffusion is what? The mass flow of atoms from the higher concentration to lower concentration. And this is the relation. That is the diffusion coefficient for the electron and holes. Yesterday, the Gaikwad sir has already mentioned about the details of the semiconductor. What is the semiconductor, PN junction? So I will not go into the details. So this is the relation which you need to, you have to write, or you should write. This is the equation which will be important. This was, I think, asked in the June 2018 exam. So this is more important. Then this law of mass actions, which is Np equal to Ni square, where N is number of electron hole concentration, P is electron hole concentration, Ni square is intrinsic character concentration. Intrinsic, extrinsic semiconductor, all of you are aware. Intrinsics means purely silicon or germanium, and either it become N-type or P-type depending upon the doping. For N-type, you have to dope with pentavalent impurity like phosphorus, arsenic, and for P-type, you have to dope your sample with aluminum, boron, so you'll get the holes. Okay, so I'll not go into details. Einstein relation, which we can say for the semiconductor. Okay, this is the relation again. You have to write. Okay, you all of you just write your notebook, so it's better to. Well, again, not going into details. Main this equation, Clausius-Mozart equation. This relation gives you the relation about the dielectric constant and polarizability. Now, what is polarizability? The ability of the molecule to polarize. Now, in case of dielectrics, again, I refer you to go for this Pillai book, SO Pillai book, in which the dielectric causes part is very much good covered. So, this relation is very much important. Dielectric constant, what we can say, dielectrics are basically insulators. Insulators in which when we apply the electric field, there is only just movement of the particle or electron, we can say, not the flow of the electrons. And the alpha E polarizability means how much atom get polarized, because normally all atom consist of the nucleus and electron cloud revolving around it. So consider it as an effective center. So when you apply the electric field, that is from positive to negative, that electron cloud will shift by some distance. Okay. Now, why electron cloud shifts with some distance compared to the nucleus? Because it has less mass for the electron cloud, and you will get the dipole separation, some separation. Dipole moment is what? Charge into distance. So there is some separation and create the dipole moment, and that dipole moment per unit volume gives you the different polarizations. Again, there are different polarization. It is surface, it is ionic, it is orientational, it is electronics. Okay, I will not go into details. These that's the polarization is like mainly consider for the electronic polarization at higher frequency. It also accounts. So for every molecule, you are getting this electronic polarization. Orientational polarization we are getting for these molecules which having the different structure. Let's say for H2O. H2O at this case, it's like a reverse switch structure. Hydrogen is at two sides and oxygen is at this, which is having the bond angle around 104 degree. So we'll get this rotation. Means after applying the field, it will rotate like this. For ionic structure at Na plus Cl minus, we'll get this ionic polarization. Next thing I would like to is the about the superconductor. What is the superconductor? Let's say I have a material. If I cool that material below a certain temperature, which is known as critical temperature, we can say, then there is sudden drop in the resistivity or resistance or resistivity will become zero. Means it's purely fully conductor, good conductor, we can say, ideal conductor. And there is flux quantization in superconductor. Before that, I will like to mention about Meissner effect. So all of you are about the Meissner effect. Whenever you cool your material, magnetic lines of holes expel out from the material, out of the material. Whatever induced magnetization is generated, that is cancelled by the applied magnetic field. So these applications mainly we can use in the magnetic elevation trains, where we can use this. Now, the temperature dependent equation of the critical field. So there are two types for the superconductor. One is type 1 superconductor and type 2 superconductor. And there is critical magnetic field. After that application of the electric field, your superconductivity will destroy. Means it not at all this temperature. Recently, one paper is there from last year. It's from the ISC Bangalore. They have reported the room temperature superconductivity, which is much more in the topic not that days. But the till now this highest temperature is got for the 90K, which is for YBCO, which is yttrium barium copper oxide. YBCO having the 90K superconductivity. So if someone wants to do research, they can go for this superconductivity. Sprintonics is there, and people are trying, lots of research are trying to develop the new material, which is also the lead free and which shows the room temperature superconductivity. If that happens, then it will be much more useful for the society. So this is the critical magnetic field, we can say, at a particular temperature. This is the SC0 is the magnetic field at room temperature, we can say, and T and TC. TC is what? The critical temperature below which you will get this expulsion of light, or below which your material acts as a superconductor. For the type 1 superconductor, there is only one critical field, magnetic field. After that critical magnetic field, if you apply, then metal will become a normal conductor. So, for that, let's say for mercury, it's around 4K. So if you supply some enough magnetic field, then it will again come back to normal mode. And in type 2, there are two magnetic fields, which is the term as Hc1 and Hc2, let's say. Before that, Hc1, it will normal act as a superconductor. Between Hc1 and Hc2, it is again normal, not pure much. And after that, Hc2, it will become a conductor. So basically, all superconductors are diamagnets. If you go for this relation B and H, B is equal to mu naught H. So whatever the magnetic induced magnetic field, which is getting the 0, that's why you are getting the chi susceptibility, which is the M by H, which is negative. So which is repelled by this. What is the property of diamagnetic? Which repels the properties. Okay, repulsion. That's why you will get the floating, the application of the magnetic levitation train, masonry effect. The next term is about this this formula. Okay, what is that? Hc1 is phi naught upon phi lambda square. Phi is what? Flux quantization. All of you know this. Now lambda is here. We can say it is the London penetration depth. Okay, it is same as the skin depth. Skin depth is what all of you have mostly studied in the ED, electrodynamics. The distance up to which, let's say I have the amplitude 100 or I, and at a particular distance, if that amplitude goes down by 1 by E amount, means 1 by I by E amount, then that distance is known as skin depth for this. And you can calculate using this skin depth, the London penetration depth. So next net exam or set exam, they have asked question from this. You calculate the London penetration depth from this. So what we have to do, you have to substitute the flux, magnetic field, phi is constant. You will get this London penetration depth. Now this is the plus quantization. Now you can see here 2E is there. It is not H by E. Normally in silicon oil drop and all those experiments, what we can do, we can calculate the E by M ratio and all those things. In superconductor, there is one effect which is known as Josephson junction. Okay, Josephson junction is what? If you take a two superconductor, which is insulated by some insulating metal, let's say. There are two effects. First one is DC Josephson effect, and second one is AC Josephson effect. Without any application of the electric field or without any bias, you will get the DC flow. This is the DC Josephson, and in AC Josephson, when you apply the DC field, an alternating frequency is generated, which is given by this relation omega, which is 2eV by h cross. Now 2e, which is the charge of the Cooper pair. Now all of you have heard about this Cooper pair, which is the theory developed by the Barton-Cooper-Schritt, which is also known as the BCS theory. So what is the Cooper pair? Whenever the electron goes into the lattice, it interacts with the lattice potential. Then electron lattice interaction causes the potential. If that electron lattice potential is much more greater than electron repulsive potential. Again I repeat, if that electron lattice potential, if it is much more grand electron repulsion, then that electron is assumed as a two electrons are combined together, which is known as Cooper pair, which is having charge 2e because 2 electron, which is act as a boson. Okay, so that Cooper pair is responsible for the superconductivity. Again, I will not go into details, the further part. So this is the frequency when you apply the Josephson effect. This is the frequency you will get, which is 2eV by h cross. That's why you are getting this 2e, the 2 factor. So again, same thing for the exam purpose. Just you can note it down. For microvolt, you are getting around megahertz. Simply for micro, you are getting the frequency in megahertz, or 1 volt, you are getting in terahertz. The time switching for the Josephson junction is about 10 raised to minus 15 seconds. Okay, these are the main things switching of the Josephson junction. Again, for the reference, you have to refer the Kittel book for this Josephson junction or superconductivity chapter. Okay. Next thing is about the Hall voltage. This is the Hall voltage which is generated. All of you know about this Hall voltage. When we apply the current flow and we will get magnetic field. And Hall voltage is basically used to charge the carrier concentration, number of mobile charge concentration. Hall effect, their Hall coefficient is there. It may be negative or positive. For metal, it is negative. Okay. Now, there is one more formula which is very important, which is number of Frankel defect. Now, there are two defects or vacancy. All of your defects means what? there is missing of the subatom. Let's say you have the crystal structure, lattice plus basis. If there is missing of the some atoms, then there are, if the cation is missing and if it moves to the interstitial site, then the Frankel defect is occur. So this is the standard formula, okay, for the standard formula. So in exams, most of the times, I think in last exam, this formula was asked. It is for 5 marks. So you can imagine how much time it will take. It take only 1 minute to mark. Or nowadays it's online, so it's take almost 30 seconds to click. If you know this formula directly. Otherwise, what you do, if you solve the quantum equation, part C, it will take almost 20 minutes and you will get same marks. So I suggest all of you to go through the detailed solid state physics and nuclear physics because it's very much important subjects. Two easy subjects. If you prepare well, go with proper understanding, you will get definitely 30 marks within a short time. Means within I think 30 minutes or max 45 minutes you will get 30 marks. So what makes you? Makes you makes you less tense or it makes you more positive. Means what you need to cover 70 marks in 2.5 hours. So that is the psychological advantage we can get, that I have got 30 marks. What I need to do, I have to just focus on this remaining 2.5 hours and I need to focus or properly click on the 70 marks. If you go up to 70, 100, and the risks you have to take in the part C, again I repeat, this part C is very important. But these are the main risk-free subjects which I can say. That's why you are getting this Frankel defect, shortcut defect. So all of you should know this Frankel defect, shortcut defects. I will not go into details. And the typical order of the band gap in superconductor is of the order of 1 milli electron volt. Again, this is the derivation. Okay, so I'm not going to details. Okay, so now we will move on to the questions. Now, till now, due to this global pandemic, the exam was not held. The June 2020. The December 2019 exam, which was held online first time by the NTA. Now look at the question. What they asked in AC Josephson effect. Okay, the superconductor current flows across superconductor separated by thin insulator regulator. They were just given the description. What they asked, the angular frequency of resultant superconductor given by angular frequency of the superconductor. So supercurrent is what? It's the persistent current, which is also known as. So it's the continuously moving. So just we have seen the frequency which we are getting is 2 EV by H cross. Again, there is one option which is EV by H cross and 2A by H cross. The 2 is come to the Cooper pair 2E. Just you have to click, you will get 5 marks, which is much more simple. You don't need to solve anything. Okay. Next question. What does for the temperature much less than Dubai temperature? This was again from December of 2019. The temperature dependence of the specific heat at constant volume of copper is given by, again using that Debye model, Petit model. What you will get, this is the relation between this AT plus BTQ. This is the AT in the electronic specific heat, and this term is due to the lattice specific heat at low temperature. Because there are different models, Dulong Petit law is there. Then one thing, Einstein model is there in order to correct those factors. Because at high temperature it's okay, it's obey. It's high temperature, it's CV is 3R. But at low temperature, the experimental results fails with the theoretical result. But the Debye model, which is the quantum approximation, which has considered the more number of electron, n number of simple harmonic oscillator, which is vibrating with the same frequency. Again, from that relation, you will get this. Okay, this is the direct formula which they ask. So means you can look, and again one question is there. Okay, for a crystal, let's find denotes energy required to create pair of vacancy and interstitial defects. You have to look at this question carefully. Vacancy and interstitial defects means which defect is there? It's Frankel defect. So just now we have seen this formula. This Frankel defect. Okay, this is N1 and 2. We can say interstitial site, lattice site, and EI is the activation energy what you require, and KBT is the constant. So which one is correct? So this first one is correct. So you can imagine in last exam, I think most of you have given this exam. How much time it will take to solve those examples? Hardly 5 or 10 minutes. You will get 15 marks. Means in very less times you are getting more marks compared in part C. So the first question you will ask about this Josephson effect formula. Second, again, if you know this Debye temperature, Debye theory, despite temperature, despite theory, you will directly click this formula. And the Frankel defects, you have to just look at this point, pair of vacancy and interstitial site. Okay. So the next question is from June 2019. Okay, 5 marks. What they ask? The third nearest neighbor distance in body-centered crystal with lattice constant is. Okay. So I think it's virtual, so I can't see all of your faces, but still, I will go into this. Now the body-centered again. I'll directly go to this solution. Okay, the body center. Look at here, this structure. This is the unit cell. Atom at the corner. One atom is at the center. Now, using the Pythagoras theorem, what we can calculate? Now, the first nearest neighbor is which? This distance. The marked distance is the first nearest neighbor. Second nearest neighbor is this distance, and third one is this one. Because this is the diagonal. It is the root 2a. So, how can you calculate it? First, you should calculate this distance. This one. First fully distance. This one is a, your lattice parameter a square plus a square root 2a square, which is equal to this one, and then divided by 2, because the atom at the center is at the center. You can just divide by 2, so you will get the root 3 by 2a. Okay. Second nearest neighbor, again we know this is at the a point. The third nearest neighbor they have asked, which is at the root 2a distance, means it's at the diagonal. Which points you have? Either any one point you can consider. Diagonally opposite. So we'll answer get the D. It is the root 2 n. In the next question, okay, this was the critical question from the dielectric constant. You should know about this theory. The formula which they requires, they are not expecting this. The bound electron and hole pair interacting via Coulombic potential in semiconductor is called an exciton, which effective mass is an electron and hole about 0.1 Me. Okay, which is the 0.1 mass of electron. And mass of hole is given how much? 0.25 Me. What they ask? The dielectric constant of the semiconductor is 10. Okay, again this is for confusion. Okay, you don't need to guess. Assuming that the energy level of the exciton are hydrogen-like, binding energy of the exciton in units of Rydberg constant. What you need to do? First, you have to calculate the effective mass, reduced mass for this Rydberg constant. This is the formula for the Rydberg constant. Okay. I think all of you have covered in this MS, atomic and molecular physics, Rydberg constant, and the energy which we are getting, it can be calculated using this. So using those formula and by substituting the values, we will get the answer. So it's like around minus 8.33. Okay, the ground state energy of the exciton, and the binding energy of the exciton is in the plus 8. The negative sign terms of the attractive potential, binding bound electron. Similar like to this ground state energy of the electron, it's minus 13.6. And the once you go from k level, let's say for n equal to 1, let's go to the higher, the less energy required to knock out that electron. For k level, you require minus 13.6 electron volt energy. For second level, you require minus 13.6 by 4 n square, so around minus 3.4 energy required. So higher you go from this state, the less energy you require. And these are the, when you go for the higher state, you will get the continuum states. In case of quantum mechanics, what we are considering the oscillator having the discrete energy, it is the quantized energy. Frequency is same, the difference in the frequency is same, h cross omega, h cross omega, h cross omega. But in case of this, when you go for the 100 level or 99 level, for 100 level, what is the formula? Minus 13.6 by 100 square. And for 99, minus 13.6 by 99 square. So there is very much little less difference. So these states acts as the continuum states. Okay, so states from the difference goes decreasing, and at the topmost point you will get the continuum states. So you will get this answer in terms of Rydberg unit. Okay, this question was asked in December 18 exam, CSIR-NET. What they asked? The barium titanate crystal has a cubic perovskite structure. Ba2 is situated at the corner, which we can see. This is the black one, which is at the corner. Then the center T atom is there. Actually, it is Ti4 plus. Okay, so Ti4 plus is at center, and the number of optical phonon modes in the crystal. Again, go back to this or previous slides. So optical phonon in 3 dimension, which is what? 3p minus 3. Okay, so using that formula, you can easily calculate it. The acoustic phonon modes which you are getting is 3 and 3p minus 3. Now, what we require? We require the p value, which is 5. How it comes? Now the effective atoms per unit cell. Like using that you can calculate, or either simply just look at this formula. You can easily calculate. How much is there? It's 3, 1, 1. It's 5. So directly you can calculate, or look at the crystal structure which they have given in the exam. For Ba2, which is situated at the corner, this atom is shared by the 8 cube. So what we are getting, it is n into 1 by 8 into 8. You will get the 1. Now this phase atoms, which is at the corner, it is shared by the 2 cubes. 1 cube at this side and 1 cube at this side. So it is 1 by 2 into 6. And there is one atom at the center, plus 1. Okay. So what you will get? Okay, so this is not required there. So plus 1. What will you get? It's 5. So the number of optical mode, they have, again remember, number of optical mode they have. So it's 3, 5 minus 3. 3p minus 3 we can say. So it's 3 into number of atoms per unit cell, 5 minus 3. So just optical bonds, 3 dimension, cubic, they have 3 dimension, you can easily calculate. For 2 dimension, it is 2p minus 2. Okay, and for 1 dimension it is 1p minus 1. Simple case. For cubic, you have to just look at the question properly, use simple logic, use the basic concept. Okay, you can easily solve the problems without wasting too much mathematics or too lengthy calculations. So you will get it 12. Next question. Okay, what they ask? The dispersion relation of the optical phonons in cubic crystal. Again remember, cubic crystal means 3 dimension. Okay, it's 3D, which is given by this omega, which is proportional to k square, where omega is constant. The contribution to density of state to the phonons. Just we have seen in I think second or third slide, the relation between the density of state and omega. Now, normal way which you can solve is using this. Okay, what you have to do? You have to go for density of state. This is 2 pi by L bracket cube, means the wave vector for 3 dimension. It's the cubic unit cell. 4 pi k square, which is the area of the sphere. Solving this equation, you will get this answer. But if you use this trick, or we can say the main crux or shortcut, you can easily solve. Now in this case, what you can do? This is the d is what? The dimension. Dimension which was is 3. So what you can do is the 3, and is s is what? Power of k, which is power of k is what? This is 2. Power of k is 2. So 3 by 2 minus 1. How much you are getting? It's this one. So without wasting too much time, too many calculations, you can easily solve. So just note it, note down this one. This is the main important formula, and the chart which I shown first slide, which is very important to calculate specific heat. Again, if they have asked for the graphing, what you will do for graphing if that relation is does not given, omega relation. For graphing, you know, which is omega proportional to what? K. Simply where it will be done for this, you will get this 1 power of k will be 1. Instead s, we have just taken 2. Instead of that, we will get into 1. Now the next question which was asked in the June 2018 exam, it was again 5 marks. In solid state, we are getting 5 marks question, 3 questions each exam. Remember, no need to check what is the pattern, what is the weightage, what are the last questions. Last page. So the NaCl, which is phase centered cubic lattice, while basis consist of Na plus and Cl minus separated by body diagonal of the unit cube. Which of the plane corresponding to Miller indices given below will not give, again look at the question properly, will not give rise to Bragg reflection of X-ray. Just before I previously mentioned, for simple cubic, all HKL planes are allowed. Means for simple cubic, all answers are correct. For body centered cubic, if your H plus K plus L is even, then it will give Bragg reflection of the X-ray. For BCC, body centered cubic, and for FCC, H plus K, K plus L, or H plus L, or K plus L, or H plus K will give this. So the next thing, you will get this. Now look at this. For this, so it should be either even or either odd. Now this is the Miller indices, which is H, K, L. Now take any combination of this H plus K or K plus L or H plus L. What you will get? 2 plus 2, 2 plus 0 or 0 plus 2 will get the even number, either 2 or 4. Same case about this, you will get the even number. This case, same thing. Either you can take H plus K, 3 plus 1 or 3 plus 1 or 1 plus 1, you will get the even number. But look at this option. If you take 2 plus 2, H plus K, you will get the 4. And for this 2 plus 1, you will get this 3, means H plus L. So it's not acceptable at all. Okay. So either it should be even or it should be odd. How much you are mark getting? 5 marks. Just by knowing this concept, H, which all values are allowed. Now the dispersion relation, next question. For the electrons dispersion relation is given. Now the electrons, all of you are proportional to K square. This is the constant, forget about this, E naught and all those things. K square, electron K square, phonon, boson, magnon, graphene proportional to K, simple. Now they ask the resonance cyclotron resonance frequency. Now the cyclotron, which is whatever the magnetic field which we can apply, that is balanced by the centripetal force, and we will get this equation omega, which is EB by m star. Now the m star you can calculate using this formula. Just we have seen effective mass formula. Now you have given this E relation. Just take the double derivative, substitute all those values, you will get this relation. So answer is 4th one. This one. So we are getting the 5 marks. Now the next question, December 2017. What they ask? They consider two-dimensional material of length L and width W subjected with a constant magnetic field applied perpendicular to it. So using that first 3 lines, what you can do? Just wait. Is it visible, sir?
No, sir.
Oh, wait. I will share again. Sorry for the interruption. Okay. So using that first 3 lines, what you can imagine, the two-dimensional material of length L, width W, subjected to constant magnetic field, which is applied perpendicularly. This question is for the Hall effect. So for Hall effect, all of you knows about this Hall coefficient and Hall velocity, drift velocity we can say. What they are given, the number of charge carriers per unit area. They have given this n equal to whatever factors k cube e by 2 pi h cross. And what they have asked to calculate Hall resistivity rho xy. Okay. Now again same thing, you can calculate easily using this relation. Rho is what your p by n, RH is 1 by n minus 1 by n. Just substitute this n value in this equation, whatever the values they have given, you will get the answer. So it's too much simple. So answer is C, 2 pi h cross by kq square. Now the June 2017, same question. What they asked, the electrical conductivity of copper is approximately 95% of the conductivity of the silver, means they have compared. The while electron density is approximately 70% of the in Drude model. Okay, Drude model, you have to consider the ohmic law, J is equal to sigma E, Ohm's law. Now what they ask, the relaxation time of copper and silver, mean collision time, we can say collision time is silver. What you can do, you just know this relation sigma, all of you should know this, n square tau by m. So if you take the ratio which is having the number of concentration given, from that you can easily calculate. So it comes around the 0.66. Okay, so last answer is there. Just compare, take the ratio of this collision time, mean collision time, you will get the answer. Second question. Okay, again, the low energy electronic excitation of two-dimensional sheet of graphene. Graphene is there, so relation is K. If it is not given, you should know it. Okay. Now what they ask, the density of state is proportional to. Again, using the same formula, you can calculate easily. Now, in this case, D is the dimension. Dimension is what for graphene? All of you know this. Now, in this case, already got 2 dimension. But graphene is 2 dimension. Power of K is 1. So, it is 2 by 1 minus 1. So, how much we are getting? It's 1. So, it's proportional to E. Look at how it's simple. Means without wasting too much time or too much in the calculations, you can easily solve. And same questions for quantum mechanics, it will consume your 20 minutes and same marks you are getting. Means more you solve. So all of you, I request to all of you solve those problems, solid state physics and nuclear physics. And if you refer the YKLM series book, you will definitely all get those problems. So you can easily crack. So and the Wahab book, which having the 500 problems, you will get it on Amazon or Flipkart. You can order. If you solve those problems, you can easily cover 30 marks. Easily cover, no problem. Now the next question is about critical magnetic field, which we have discussed for the superconductor. At temperature 4K is there, one is given, and 8K, which has given 11 milliampere per meter and 5.5 milliampere per meter. On the transition temperature, they ask. Just we have seen this relation. Critical magnetic field at particular temperature at 0 field, you will getting this relation. So just substitute the values at T1, which we are getting this one 11. So we will get this answer finally 10.6K. Now there are lots of different problems are there. I have just taken the different types of the problems, so you will get idea about this solid state physics in CSIR-NET. Now next I will cover the problem for the Maharashtra state exam, which are much more simpler, or we can say the cream part. It's not going to the deeper level. For NET exam, you have to, if you want clear basic concepts, you know the crux, we can say the important points or the formulas, you can easily crack. For set exam, they will ask the basic definitions and all those things. We will check this some examples. Now, what they ask, for the ideal Fermi gas 3 dimension, the electron velocity of the Fermi surface is related to. Now again, the first table which we have drawn for the 3-dimensional, again it comes to this 1/3. For 2-dimensional, it is 1, and 1-dimensional it is 1/3, 2/3. So they just make that table. Okay, you will get the idea. Next question is what? Which of the following cubic is most loosely packed? Now, most loosely packed means in terms of the atomic packing fraction. We can see means how much atom is closely packed. You can calculate using that volume of the units, volume of the cell divided by volume of the unit cell. Volume of the cell is what? Now you can say this 4/3 pi r cube. R is different radius, which is different for simple cubic, body centered, and FCC. And A cube is the volume of the unit cell, whatever you consider. Now, if you calculate all those parameters for the simple cubic, now mostly what we are assuming, simple should be less. Body centered, FCC we know. For FCC there are lots of atoms. BCC, 4 atoms per unit, 2 atoms per unit cell. Simple cubic, 1 atom per unit cell. But the diamond structure, which is most loosely packed, which is having the packing fraction around 34%. Means the diamond structure, if you look at this, there's the position at the 0, 0, 0, and 1/4, 1/4, 1/4. And there are 4 atoms at the unit cell, which is having this position 1/4, 1/4, 1/4. Or if you look at the bottom side, you will get this quadrant 3/4, 3/4, 3/4. So the diamond is most loosely packed, having the packing fraction 34%. So just write down for simple cubic, it is 52%. For body centered, it is 68. For face centered or hexagonally close pack, HCP and face centered, it is same 74%. And for diamond, it is 34%. I hope it's clear all of you. The next question, now in state exam, what they will do, they will ask a bit more lengthy questions. So we were just little bit worried, oh, what is that question, it's too much lengthy. Let's just look at the main points. What they ask, the flux side, flux they ask, this is given, flux is given, type 2 superconductor, we know this. The strength of the magnetic field at this point means Hc is also given. Now the penetration depth or the London penetration depth. So using this formula, just we have given Hc pi by pi lambda square. You can substitute the value of the pi. which is 2 into 10 raised to minus 7. This value you can substitute. Hc goes this side. Hc you can substitute this 2 pi 10 raised to 5 was, and you will get the lambda. So the answer which you are getting is 100 angstrom. Is for set exam, you need to just look at all the formulas. You can make a list of the formulas. You will definitely get the answers. Now the set 2018, Maharashtra set 2018. What they ask? The density of state of the conduction band for electrons assumed to be essential in 2 dimensions. Look at the question properly. Which dimension they have mentioned? You have to look the dispersion relation and the dimension. Main thing. The 2 dimension, all of you know, it is the independent of energy. For 1D, it is e raised to minus half. This is for 1D. This is for 2D. Sorry, this is for 3D. E raised to half. This is for 3D. So for 2D, you are getting independent of energy, independent. Now, again, same question, depending upon the concept. In allowed band of semiconductor, effective mass of the electron is infinite. Look at the diagram. Remember the diagram. Effective mass at the point of inflection, just as I said, at the middle of the energy band, you will get effective mass infinity, because this is the point of inflection at which you will getting the derivative 0. So the second question again looks a bit more lengthy, but what they ask, the frequency of the lattice wave in terms of wave vector. Again, this is the standard formula. You will get derivation from this optical branch, acoustic branch. After solving all those brood theory, you will get this equation for 1 dimensional at least. Okay. Next question. The order of magnitude of the energy gap of the typical semiconductor is. For semiconductor, we should know, should not be in mega, it should not be in kilo. There is confusion between electron, mega, milli electron volt. So it's milli electron volt. Now this question. For primitive given unit cell, 2-dimensional lattices, which option lists primitive cells? Look at the question properly. Primitive cells means what? Number of atoms per unit cell should be 1. Look at this figure first. Okay, there are lots of options. Now, in option, what you need to do? You have to first confirm option which is the common thing. If that option is not there, you can easily neglect, and the more the probability you will get the correct answer. Means what? In this case, it is not as the 4 option is not there. In this case, 4 option is there. In this case, 4 option. So if you look at the 4 option, these 2 may get automatically answer. Look at this 4th option. Now, is it a primitive cell? Yes, because it is not connected to the corner, and there is one point inside this unit cell. So if you calculate, the number of lattice point per unit cell is 1. So 4 is there. Okay. So what you can do? 4 is there. Now look at this 5 number points. For this point, all of you know this. 4 atoms. 4 atoms at the corner. Number of unit cell per is 1. This again same thing. This two tilt rectangle still same. For this atom again, atom is at center. No, it's touching. For this atom, look at this atom. There are how much atoms are there? 1, 2, 3, 4, 5, 6, 7. 6 atoms are there. So the number of lattice points per unit cell for the corner will be 1 at this atom, which is shared by the another unit cell, which we can say. So this contributes half and this contributes half. So this number of lattice atoms per unit cell in this point 5 case, which is 2, which is not primitive unit cell, which is primitive non-primitive unit cell, we can say, which is not primitive cell. What they ask? Primitive unit cell. So you can take this option easily. Now the relative magnetic permeability of type 1 superconductor is magnetic permeability. Okay, magnetic permeability. They ask. Now for superconductor, this is the relation. What we can do? U is equal to 1 plus chi. Now chi is what? Susceptibility. For superconductor, I already mentioned, is of the diamagnets, in which the induced magnetic fields cancels the applied magnetic field. You will get the B0, and chi is -1. So 1 minus 1, you will get the 0 answer. So first option is correct. For the next question, what does in long wavelength regions of the magnon dispersion relation 1-dimensional they have asked? Okay, so it's proportional to k square. Now the Fermi energy of the intrinsic semiconductor lies. Fermi energy of the intrinsic, it should be the middle of the band. Normal. Whenever you go for the n-type semiconductor, it moves to the conduction band. For the p-type semiconductor, it moves to the valence band. And for the intrinsic semiconductor, means undoped, we can say pure silicon or germanium, it is at the middle. Then the next question was asked from this is the mechanical system and identical spin half particles, which is almost fermions half particles in 1D box, the Fermi wave vector. Directly they have asked the questions. So we have again checked that using this table, we have again calculated this formula. Okay, so what we can do? Okay, sorry, this one is correct. Iron by 2. If you calculate this, all solves the Sommerfeld model using the Schrodinger equation and boundary condition, you will get this answer. So what you need to do, you have to just look at that table, the first table which you are shown. You will get the easy answer. Same thing in second question. The same ask about this size of the primitive cell. Okay, same question. For 2 dimension, if you know this care, you can easily calculate. For 2 dimension, it is root 2 pi by a. You can easily calculate this one. And for this one, 1 dimensional, it is pi n by 2n. And for 3 dimension, it is 3 pi square n by l. You can easily calculate. Now look at the next question. Okay, most loosely packed. Okay, we have covered this. It's diamond. Now next question. The ratio of the skin depth in copper at 1 kilohertz and at 100 megahertz approximately. Skin depth, again I repeat, the distance up to which your amplitude is goes by 1 by e amount, or it decreases by 1 by e amount, e, which is having value 1.73. So e amount. So that distance you have to calculate. So this is the relation. This is the skin depth delta, and it's inversely proportional to the square root of frequency. So using that ratio, you can calculate. It comes around the 300. Now the set 2017. Directly they have asked the formula for transition temperature in case of magnetic Hc1, Hc2. So which one is correct? Is the fourth one. Now the next question is total number of Na plus Cl atoms in unit cell. So Na plus and Cl atoms per unit cell will be 8. NaCl, it is the interacting FCC lattice, two interacting FCC lattice. Cl is situated at the corner. You can look at the structure, so for better understanding. And Na plus is at this, we can say middle of this. So from that you can say 4 Na atoms and 4 Cl atoms. They ask the total atoms plus. So if they ask for Na plus, you will get the 4 answer. For the total atoms NaCl, you will get this 8. Now the next question is okay. This question we also covered. Next question is the packing fraction of the diamond. Now, in this case, what they ask the value. In previous case, what they asked, which one is loosely packed. Next year, what they asked, the diamond structure packing efficiency. Again, the same thing. If you know the values, you can directly click. Or what you need to do, you have to calculate the packing fraction using the volume of unit cell divided by this volume of unit total area. You have to substitute the radius. You will get this equation. So note to this, for diamond you will the 34, for simple cubic you are getting this 52, this is for body centered 68, and for FCC you are getting the 70. And for HCP, hexagonally closely packed, you will get the same answer. Okay. So for FCC and HCP, hexagonally closely packed, the packing fraction is same. Next question is from the if the silicon crystal is lightly doped with boron, the silicon will become. Now with boron is trivalent impurity. So again, it become the p-type semiconductor. If we have dope with the pentavalent impurity, like phosphorus, arsenic, it will become n-type semiconductor. Now in this case, aluminum or boron, so it's become the p-type semiconductor. Now the frequency dependence, next question, the frequency dependence of the electronic polarability, which is much more related to this Clausius-Mozart equation. Electron having a resonance frequency is given by, again this is the standard one, which is comes after the long derivation of this model, root model. You will get this relation, E square by m and this one. So I hope it will be clear to all of you. I have just taken the main, what we can say, the glimpses or the crux points of this solid state physics. So I recommend all of you to go with this Vaikilim series book and Wahab book for the better understanding of these concepts. And it's simply easy one. If you do properly, conceptually proper ekdam, then and then only you will get this marks. And you have to just look at the question carefully. It's easy one, but you have to look at the dimension and the dispersion relation power. Then and then only you will get this solution. And the one thing I request all of you that if you are not good in the solid state, you can just start from today onwards itself. So better you go for the first SOP live book, which I recommend all of you. It will be good for the basic understanding. Then you can go for Kittle, then and then only you can go for Weikel. Don't directly go to the Weikel. It's uh, it's a good one, but you will not get the. If you know the basics, then you will can easily solve the problem. And Wahab solution is also good. You can buy it online because nowadays we are all stuck at our homes. You can buy it all return online. So thank you all of you. I hope due to time limit, actually I'm not able to cover all this problem. But still, in future, Dole sir will surely make a long
Sure,
session.
sir. Sure, sir.
Sure. Thank you.
Thank you very much for your first session, sir. There are some questions. Can I ask you?
Yes, sir. I can check in chat box. No?
Sir, it is sent to privately.
Okay, you can. Yes.
Yes, sir. The questions are, the more questions are not related to SSP, but they are asking more general questions.
Okay.
Veer is asking how to prepare for different questions in every new exam. No idea what comes next.
Okay. So the main thing is you have to look up the all points. Now just points I have covered.
Yeah.
If you know that chart, density of state, it always help you. And it's thought we should not consider like it will come in net exam. It will may help you in gate exam or set exam. It's not like that. It will definitely come exam. Let's say somewhat saying the group theory, or in case of mathematics, there is one question which will told now इस साल ये आया है उस साल ये आएगा. So ऐसा नहीं होता. We can't predict because the pattern should be different. Now it's online, so it's totally shuffle questions. It's easily one, and it's there the burden of the countdown. You have to again look at the question that how much time remains, is the clock countdown time. So again, I refer all of you to look at the all syllabus, and basically you can solve those. So it's not like that which question will can predict, even though we can also not predict which question will come. But definitely, if you cover the basic points or the basic the shortcuts, which I said shortcuts or the cream part, then you can easily solve this. And it will definitely help you in different exams. Not if not set in exam, you can calculate set or gate or just. It will definitely help surely in future.
Okay. The next question is from Mukul Saraswat. Please suggest a book for XRD pattern study.
Okay, so for XRD pattern study, you can go for this BD quality book. BD quality. I can type in the chat box. If, okay, wait. BD quality. You will get it online. I think it's available. You can download the PDF copy and you can read it.
Yes. Can I ask the next question, sir?
Yes, sir.
The next question is from Shivani Gawande. She wants to ask, please repeat the hint for knowing whether the given Miller indices give Bragg's diffraction.
Okay. So for simple cubic, again I repeat, for simple cubic, okay, or I will go to this slide so better you will understand. Okay. For simple cubic, all HKL planes are allowed. It's all H plus K plus L, and H plus L values are allowed. Now, whatever things which they have given, these are Miller indices. Means this one is H, first one is H, K is 2, and L is 0. Now, in simple cubic, it will rise to the Bragg reflection for all planes. Now, in this case, what they have mentioned, so that's why I'm saying look at the question properly. Face centered cubic. Now, for if they have CSIR, which is the body centered cubic, For that, h plus k plus l should be even. Means this 2 plus 2 plus 0, which is 4. It is 2 plus 4 plus 2, which is 8. 2 plus 2 plus 1, it is 5. And 3 plus 1 plus 1, it is 5. So for body-centered cubic, if the h plus k plus l values are even, then that Bragg reflection is allowed. Now, in this case, what they ask face-centered, somewhat directly click on all the options. But look at the question properly. Will not give. Again, main thing is face-centered and will not give. So in this case, 2 plus 2 plus 1. Now, if you calculate h plus k, it gives you 4. H plus L gives you 3. And K plus L gives you 3. So it is mixed structure. It is either even, neither or, it is mixed structure. So that's why this Miller indices is not allowed for this case. In all this case, you are getting the even values. 2 plus 2, 4. In this case, you will getting 8. In this case, you will getting different one. H plus K, K plus L, and H plus L even value. Just in this case, if you look H plus L, it will give 3. H plus K will give 4. That's why it is not allowed. It is the mixed plane, we can say. Hope it will clear.
Okay, okay. Thank you, sir. There are some few questions and few participants are raising their hand. I request all the participants, due to time limit, Ramdasi sir will provide all the answers through the email. They will provide
Yes,
email at the second session.
sure.
Thank you, sir. At what time we will start the second session, sir?
Around 2:15 after a hour.
Okay, sir. Thank you. So participants are requested, they can leave the meeting now and they can rejoin the meeting with the same meeting ID and password on sharp 2:15 p.m. Thank you. The next session will start sharp at 2:15 p.m.